Now we're going to have a look at uniformly accelerated motion. So uniformly means constant, it's not changing, even rate of acceleration. Acceleration happens whenever you have a change in velocity. So that means not only a change in the speed part, but also maybe that acceleration is a change in direction. So you could have something traveling in a circle at a constant speed, could be going 6 meters a second in a circle, but because its direction is constantly changing, it's undergoing acceleration the whole time. So acceleration is not just a change in the speed part of the velocity, not just in the magnitude, but also the direction. So the easiest thing for us to see accelerating at a constant rate is if something's dropped and you let gravity accelerate it. And it accelerates it at a constant rate of 9.8 meters per second squared. So that means for every second of falling, so here I am dropping something off a cliff. At the end of the first second, it'll be going 9.8 meters per second. In the next second, so that's 1 second, 2 seconds, 3, 4 when it hits the bottom. So the end of the first second, it's reached, if it started here at 0, 9.8. And don't forget, I forget myself, this is the old-fashioned way of going per second. More modern people and modern textbooks will do it like that, meters per second. It's exactly the same. So at the end of this first second, 9.8 meters a second. It's accelerating at the same rate, so that means it will get another 9.8 meters per second faster in the next second. So at the end of this, it's 9.8 by 2, which is what, 19.6? I'll try and remember to write the meters per second the way that your textbook does it. 19.6. The end of the third second, there'd be another 9.8 added on to that. What does that make? 9.8, 29.4 meters per second. So each second, it's getting 9.8 meters per second faster. So the acceleration equals 9.8 meters per second squared. That's got its own special symbol, g, because it's a constant that we use for lots of things. So g is the acceleration due to gravity. Right, and if I was to graph that, one, 2, 3, 4 seconds, and I'm only going to do 2 there. So I would have 1, 2, 3, 10, 20, 30 meters. This is my displacement. So 0, 0. 1 is 9.8. 2 is 19.6. 3 is 29.4. Right? I would get a nice straight line. Which of course I would have used a ruler to line in, but I need 2 hands to use a ruler. Nice straight line. Oh, did you find my mistake? Here it is. It's not displacement, that's velocity. Duh. I'm going to find out the displacement a different way. So that's velocity in meters per second. Righto, so the slope of this graph is rise over run, which is change in y over change in x. So it's going to be the change in the velocity divided by the change in time. So So if I'm looking at the units, that would be meters per second divided by seconds again. So it's meters per second squared, which is acceleration. Right, so slope of a velocity time graph gives me acceleration. Now there's something else I can work out from a velocity time graph, and that's the area underneath. So this area here, the area underneath the curve. So if we look at area is, in this case, it'd be a half base by height, wouldn't it? So it's a half. Base is seconds, and the height is meters per second. So the seconds are going to cancel, and we're going to have meters. Whatever the base was, what is it? Time by velocity. And we're going to end up with displacement. Half base by height for a triangle. If we multiply the base, we're multiplying time or seconds by the height, which is velocity, meters per second. Seconds will cancel. That'll just leave you with meters. So you've actually got displacement. So it'll give you the displacement. So velocity time graph gives us two things. The slope will give you the acceleration. The area underneath the curve will give you the displacement. So we could actually calculate how far that fell in those 3 seconds. And it'd be a half of 3 times 29.4. So about 15 times 3. Is that right? Roughly 45 meters. Okay. Right, so your textbook goes through some ideas like that, talks about velocity time graphs. This is useful up here. This is uniform acceleration in 3 different forms. So if you've got displacement, remember the symbol for displacement is S, not D. Displacement versus time, you're going to get this smooth curve like this. So in the first section, it travels about 2 meters. The next second, it's traveled about 3, and the next second about 5, then a bit more than 5. And by the time you're up to this second here, it's traveling about 10 meters. So the distance it travels is getting bigger and bigger, and it's getting bigger and bigger in this constant kind of smooth curve. If we look at a velocity time graph with uniform acceleration, it's going to be a straight line. Remember, the slope can be found. That will give us acceleration here. And an acceleration time graph with a constant or uniform acceleration will just be a straight line horizontally. Right, sometimes you'll get a graph like this where part of the graph is positive. So, for example, somebody jumping, they've talked about a bungee jumper. So they've jumped off the tower and gone down. Then they've sprung back up. So if this is a bungee jumper, this is him falling down is the positive direction. He's falling down. Then he must have a really springy bungee because he's going to come up and past his original position. But anyway, let's just ignore that. He's gone down. He's sprung back up higher than he was to start with, which is impossible. Gone up above that height and then fallen back down to the original height. So if you were working out the area under that graph, the displacement, in this case, the areas would come to the same, I think. Oh no, the acceleration doesn't have to be. You'd have a negative area here. So it goes through there, an example of cases where the velocity becomes negative. And then the relationships are shown here again in the summary. Displacement versus time, that shows you a constant acceleration. This is typo, that should be a T. Velocity against time, or velocity versus time, you get a straight line for uniform acceleration, and acceleration versus time, horizontal line.